So for us to be prepared for the next generation of ICS-specific malware, there are some trends and characteristics that we need to understand and look back on to be able to be prepared for those that next generation of ICS-specific malware. And one characteristic in particular is this tendency you will see of these malwares utilizing proprietary protocols. We can go back as far as Trices, and we can also discuss some of the Rockwell CIP vulnerabilities that we've seen. And I know some of you may be thinking CIP is a standardized protocol. Yes, it is. However, the attack tools that were developed to target this protocol actually targeted the proprietary CIP objects within this protocol. And if we go back a little further to the pipe dream malware, and more specifically what I focused on, which was Bad Omen, Bad Omen utilized this unknown proprietary protocol known as the NEX protocol. Now, I had mentioned that, I worked on the pipe dream malware and Bad Omen, and initially what we wanted to do was try to get some detections out, and that required analyzing not only the malware, but the sources that they potentially, CHERNOVITE, I'm speaking about the threat group, potentially utilized to build this tool set. And what we realized was that basically they just ripped out the functionality out of the EWS software, Symac Studio, and built a command line tool out of it, essentially. And while we were trying to compare traffic between the EWS software and the malware, we started noticing something very peculiar, and that is the fact that there were a ton of commands that we were seeing coming out of the EWS software's traffic that we never seen in Bad Omen. So the question immediately came to us that, what does Bad Omen 2.0 look like, right? If they create another Bad Omen, will they utilize these commands that we're seeing? What is that protocol? What are those additional commands? How extensive is it? What can it do? And I know you're probably thinking, like, this is a malware, not a movie, right? Like, how can you have a Bad Omen 2.0? Well, there is precedent for this. For example, Indestroyer and Indestroyer 2. So we've seen the precedent there. Now, before we get into the nuts and bolts of, the actual findings and into the details, I want to kind of glance over our high-level findings. And basically on the right, what you're going to see is we found the hard-coded credentials, undocumented protocols, we found remote shell commands, we found a runtime debugger, we found a bunch of vulnerabilities. But the part I want to spend the most time on is how we employed this particular protocol and some of the commands to actually impact operations in the demo. Now, back to the protocol. If you Google NEX protocol, I guarantee you won't find anything, because outside of Omron, it just doesn't exist. Our research, what it uncovered was 170 undocumented protocol commands. And if we compare that to Bad Omen only utilized 30 of those commands to carry out its attacks. Now, this protocol is a legitimate protocol. Like I mentioned, it's for the EWS software, and it's basically designed for Symac Studio to be able to control, monitor, program, etc., the PLCs and the Omron NX NJ series PLCs. And this protocol does require authentication. However, like CHERNOVITE, Dragos discovered those hard-coded credentials as well. Now, if you want to boil everything down, the root cause is basically two major issues. Number one, I mentioned the hard-coded credentials, right? These credentials are used to authenticate with a CGI server or HTTP server on the PLC, and as well as some encryption keys that's used to encrypt file transfer commands, right? So the payloads of the file transfer commands are encrypted, and those encryption keys and credentials were hard-coded in Symac Studio, and we found them in the Symac Studio binary. The other issue is the fact that that HTTP server that receives those commands on the PLC has root privileges. And this is very common in OT, ICS, IoT, digital embedded systems world. You see it all the time. These web servers will have root level access. And what that basically means is that any vulnerabilities that we find, it could be in the HTTP library, it could be in the underlying commands it receives, but any of those vulnerabilities will result in root level remote code execution, right? So this is a very bad problem. So how did we find 170 commands, right? Basically, I beat the PLC into submission. What we did was, while we were analyzing Symac Studio, we came across this particular function that was responsible for HTTP status codes, and for non-technical folks, that's a common one, 404 not found. It's basically a HTTP server's way of saying how your request went. But there was one in particular known that was the invalid command error. And when I seen this, I immediately went, aha, okay, what I'll do is I'll get the firmware, I'll rip all the strings out of it, I don't care what it is, and I'll just blast the PLC with requests, and if it says invalid command, all right, discard the string. If it says anything else, it's probably a command. And basically, that's how we came up with the 170 commands. So we just built a glorified fuzzer. So I mentioned that we found a number of protocol vulnerabilities. The first set of vulnerabilities we found were related to directory traversal. Now, those commands, file upload and file download, were actually utilized by Bad Omen to transfer files. It's used by Symac Studio as well to transfer logic and configuration to and from the PLC. Now, the issue with this particular vulnerability is that, and I'll show you in the next slide, basically, if you pay attention to line 1, that is a plain text version of the command. Now, you'll see user PG. Now, that user PG is just a file type identifier. Like, for instance, they may use it for like a compiled ladder logic binary to download it, to send it to the controller, right? Basically, underneath the hood, that file type identifier is mapped to a hard-coded directory on the PLC. And if you go a little further, you'll just see that underneath the hood, basically, it just takes that file, that directory, and appends the file name to it. So all we have to do is just, skip and hop our way back to the root directory, and you can see at the bottom that we actually were able to write a file to the root directory on the device. Now, you're probably looking at line 4 like, what is that? So I said I wasn't going to do this, but I'm just going to go for it. So what do vendors and speakeasies have in common? Any guesses? They love using backdoors. Some of you may have seen my infant last night. I've only been a dad for 2 years. We have a Dragos Slack channel that we post dad jokes, and I'm still working on mine, so we'll see how it goes in the future. But to save you from your cringiness, that console command right there, that was actually disclosed. It was disclosed in our initial reporting of Bad Omen, and it was used by Bad Omen to enable a telnet interface. Now, the one thing about Bad Omen that was weird was that they kind of did a lot of backwards things to upload and download files to it, and they would have just kept looking a little further. They would have found that these things were a lot easier. I'll touch on that in a little bit. But that com command, as you've seen, allows me to actually execute operating system commands, right? As well as the console command. So you're probably wondering, what's the difference? The difference is com is not designed to execute shell commands, but it can. It actually gives you access to a runtime debugger that has over 250 commands. Now, I had mentioned there was 170 protocol commands. So the runtime debugger can do everything that can and more. But we didn't spend a lot of time digging through all those commands because A, it was just too much. B, I was trying to understand the protocol. And the little bit I did play with it, there are more issues in there, but Omron has taken care of that. So, more backdoors. Technically, you could consider this a path traversal or directory traversal vulnerability, but I consider it a backdoor. And here's the reason why. It's 3 reasons. Number 1, well, let me back up a little bit. The file transfer, there's file transfer commands, right? And there's 4 of them. One can read, one can write, one can delete, and one can just list directories on the PLC, right? But one reason I know this is a backdoor is because I double, triple, quadruple checked in Symac Studio, and I did not find a single one of those commands anywhere. So that was the first problem. The second problem is I had mentioned the previous file upload and download commands, how it had that command line argument structure where you had like that file type identifier. You just send root, paths to that command, and you can go anywhere you want. There's no file type identifiers. And I think the biggest giveaway is the fact that if you paid attention to that other slide, I'm not going back because I don't want to give too much. Like you have it on your on the Wova app, you can look at it. But if you go back and you look, you can actually see that the actual payload that's sent to the PLC is encrypted. This command is plain text. There's no encryption. Not for the files, not for the arguments. So that led me to believe that these were backdoors, and I confirmed that they were backdoors. And this is a classic example of insecure by design, and yeah, not good. So I had mentioned, right, what I wanted to talk about was how we could utilize this protocol to impact operations. Now, I'm not going to go through all 170 protocols, and I promised Omron I wouldn't release that to the public for obvious reasons. However, I did share with them that there are some important things that I want to talk about because I want to demonstrate how maybe a Bad Omen 2.0 could utilize some of these commands that the initial version of Bad Omen didn't use. So let's back up a little bit. For those of you who may be familiar, Jimmy Wiley is one of our malware analysts at Dragos. Me and him worked tirelessly on analyzing Bad Omen, and he demoed a Bad Omen demonstration at DEF CON in 2022. And all right, bear with me. This is how this demo went, right? We wanted to manipulate the speed of a servo using Bad Omen. So we used Bad Omen to pull the logic from the controller, to unpack that logic and configuration. We then had to find the compiled ladder logic binary. We had to find the function related to controlling MC move relative, which is the servo function, the logic block that we use in our demo logic. We then had to find the value that controlled the speed of the servo, and then we had to inject code into the binary, repack it, and then send it back to the PLC. Now that is a very complicated attack. Whatever we do is static, and any engineer with a brain will notice their PLC and their operations going from run mode to program mode back into run mode. So it's a very complicated attack, and the results are permanent, right? So once we set that servo speed, that's it. So I was wondering if this protocol had any way to be able to, manipulate that on demand, right? And that was the goal of this attack. Now, before we get into how we went about doing this, here was our lab setup. And basically what we have is a PLC, I'm sure you guys know what that is, a servo drive that just controls the servo's speed, torque, acceleration, etc. And then the servo is just an electric motor that has precise control. So it can, you see these things everywhere from conveyor belts to, cooling vents, open and closing cooling vents, maybe even like open and closing pressure valves, things like that. If you go upstairs to the ICS village, you'll see a ton of servos. And basically any operation you want precise motor control, physical motor control of something, you would probably employ a servo. Now, here is the logic that we implemented. Now, I am by no means a control engineer. I do not know how to make things work. I know how to break things. And me and Jimmy wrote this code over some beers and watched a little YouTube video. And basically, we wanted something that just would make the servo go. We just make the stupid thing spin, and we just wanted a way to be able to validate if we did something, right? That we would be able to realize that in the physical world. So if we increase the speed, we want to see it spin faster. And basically, all you need to pay attention to is that box 1 is a timer. And it says every second, power on this. And at the bottom, there's that MC move relative. And basically what that's going to do, it's going to move our servo a certain distance, at a certain speed, at a certain acceleration, and stop it at a certain deceleration. Now, what's important is you see those variables, test this, speed, test acceleration. Those are inputs into that function block. This is different from the original experiment we ran at DEF CON. The original experiment, that 120, that 40, those values were statically programmed into the logic block. So it was statically programmed in there, and those variables that you see were not inputs into that logic block. And that's important because in our early testing, we weren't able to actually use these commands to read and write those values. But once we used variables in place of those with default values, we were able to manipulate and read the values in the runtime memory. Now, these two commands you see are one of like 6 different variations of the same command. This is just the easiest one for a human being to to use. And the important takeaway about these commands is that it's kind of misleading because you see memory read text, memory write, you immediately think like, oh, he can read and write anywhere in memory. That is not the case. These commands are a pain in the butt to figure out for me to reverse engineer, and it required getting some very specific variable data about our logic. So in order to execute this command, you have to have a few arguments. You need a tag revision, which is basically a way for the PLC and Symac Studio to like agree on the state of the tags. Because for instance, you can upload the same exact logic to a PLC, but addresses and offsets and things like that may change. So this tag revision is the way for the PLC and the Symac Studio to agree. The other thing you need is a count, and we'll get into that later on, but basically one command can write multiple variables at once. However, for each variable, you need this information right here, and basically those are like different characteristics that the runtime needs to know before writing or reading a variable. Initially, the way that I had to figure this out was using that com command and that runtime debugger, and it was a pain in the butt because none of the data was structured. It was just like these giant dumps, as you would imagine, for a debugger. However, I found this little handy command called variable browse info, and you send that sucker to the PLC, and it will send you back every single variable inside the entire runtime environment. So that was very handy because then I can just nail down the exact variable I needed. Now, so we created a basic proof of concept. And what this basic proof of concept was supposed to do was just to see if we can write the variable. Now, I don't have any actual code because I'm not allowed to share POCs. That's not what we do at Dragos. But you can see the plain text versions of the commands. And what you'll see is that first command, memory read, obviously we're reading the variable, right? And you see it's 5.0. Now at the time, that's 5 degrees per second. And at the time, the logic was programmed with that at 5 as the default value. The second thing we did was then try to write that value. Now we had to convert 10.0 into real because 10.0 is a float value, it's not real. So we had to convert that into real. We sent it, then we read that variable again, and then we realized, okay, we were able to change the value in the runtime. However, I did this from my home in Atlanta, Georgia. That PLC was at HQ in Baltimore, Maryland, and I had no way to actually verify that anything was spinning any differently, right? So the next order of business was to create a more destructive proof of concept and basically fly to Baltimore and figure out if things were actually spinning. So I went to Baltimore, went to HQ, and basically I wanted to slam the gas and slam the brakes. So I wrote this function that basically what it did was set all of those input values to extremely high numbers and then see if it makes the servo spin any faster. And then I wanted to set everything to like 1 degree per second and see if it slows down. And spoiler, it worked. And I had this grand, like minute-long demonstration video, and it had like Symac Studio on one side, and it had, you know, the servo video on the other side, and it had pointers, and boxes, and stuff. But then it was like, you know, that's too much for this format. If you want to see that video, you can come meet me upstairs at the Dragos Lounge. But instead, I figured a better way to make this point would be to use this. So this right here, this is your servo. All right, it's spinning, you know, 120 degrees, 120 degrees. That's what we would consider our normal operations, right? After, this is your servo on drugs. That's after the attack. So as you can see, if that's happening in your environment, right, that's not a good thing. So is your servo on drugs? What happens when your servo gets hooked on the stuff? Most likely just turn, you know, a robotic arm into like one of those arm flailing tube men you see at car dealerships. That's the most likely scenario. A more advanced threat could maybe throttle a pressure valve, open and close some coolant vents. And a highly capable threat that maybe, let's say they got access to the project file and they can actually understand your logic and know all the variables and what they do. They could potentially, you know, manipulate your physical process without, you know, detection. And we're not going to talk about that. Let's go to the next slide. Technical takeaways, right? So what are the takeaways? Default credentials is a solved problem. And I don't understand why we keep seeing this issue, but just generate a unique default password for every device and don't use, under any circumstance, hard-coded credentials. The other things is I understand vendors need their backdoors. And I know that's kind of weird to say out of your mouth, but if you understand how expensive these PLCs are and you understand they need a way to warranty and service these devices, these backdoors, you could justify having them. However, they should not come from the factory activated by default. Because whether, vendors know it or not, advanced threat groups or just like basic script kiddies like myself can reverse engineer those things and figure out the protocols and find those backdoors you put there and utilize them. So hardware keys, hardware jumpers are great mechanisms to prevent, these things from happening, from them being exploited. Now, the other point is always restrict access, root access from your end user. In better words, any service that is accessible outside of your PLC should not have root access. It should not. Because what it means is if any of that software has vulnerabilities, you have root level remote code execution. And I know this because I accidentally bricked one PLC trying to install a rootkit on it. So that's how I actually figured that out the hard way. And also, sound logic and safety systems can actually reduce the effectiveness of these attacks, right? So if you do have a situation where that servo needs to spin consistently at a consistent rate, albeit statically program it. And of course, safety systems will keep that robotic arm from, knocking out your controls engineer. So I think the biggest takeaway is, threat groups will continue to target non-standard protocols. Vendors can keep trying to hide them. They will keep being discovered. And that's why it's important to make sure you scrutinize those proprietary protocols internally and make sure you are doing the basic things right. And another takeaway is Dragos does intend to remove this stigma around vulnerabilities. Omron was great. Shout out to Douglas Brown at Omron North America. Actually, the Omron Japan engineers and PCERT teams hopped on a call with me. They were awesome. However, there's always, when you're doing this job as a vulnerability analyst, there's always a little bit of a apprehensiveness to work with security vendors when disclosing things, and I understand it. But I want vendors to understand that vulnerabilities aren't what you should worry about, right? They're not the problem. The real problem are the attack tools that get developed by those vulnerabilities. So that's it. I don't know what happened to my questions text, but we'll open the floor for questions.
Hello. Great presentation. Thank you so much. With this knowledge you have of the inner workings of the PLCs, do you believe that it's possible to create ChatGPT-like or AI versions that can create a stage 2 or stage 2 attacks, by understanding how the PLC works and the torque things you have done that rotating the torque, making much more complex and much more destructive just by pulling all this information? Is that something we will see in the future, this research being used, feeding it to an AI, generative AI, to create very complex actions in manufacturing systems? You see it happening, or you see this very, very far away?
I don't know if you attended, but I did attend the autonomous AI talk earlier this week, and I thought it was pretty interesting how he was able to automate a lot of operations. However, I don't see our adversaries using AI to do anything, and until we start getting indicators of that happening, I wouldn't suspect they're using AI to develop malware. Now, using AI to help you understand a protocol and help you in the reverse engineering process and the tool building process, maybe, but to understand how to manipulate and control an environment, I don't see that happening now because, our threats are advancing, but I haven't seen them advance to that yet.
I think that's all. Thank you so much, Logan.